All right, it's 11:15. I think we'll get started. Any questions or comments? Anything you want to say? Yes. Awesome. It's nice outside. Yeah. Except it's only Wednesday, right? If today was Friday, it'd be better. So that's right. Any other questions or comments? Okay, don't forget your homeworks, don't forget your PLAs, and we'll keep doing that. So the slides for the final, or not for the final, for exam 4 review are posted on the OneDrive. So check those out. Again, we're going to review on Friday, or Monday, sorry. Any question that you want to ask before the exam, ask it on Monday. And I've included in those review slides extra office hours. There'll be extra office hours on Monday and Tuesday in preparation for the exam on Wednesday. So there shouldn't be any surprises, but make sure you check out those review slides on the OneDrive for exam 4 before you ask me when office hours are, because the details I think are in there. And if they're not in the review slides, just let me know, because I know I made a slide on office hours. Whether I posted it or not, we'll see. But anyway, we'll review on Monday. So any question, bring your questions. I will post the practice exam as well, so you can check that out. You can get familiar with the equation sheet, all that stuff. Of course, lots of people ask good questions about the practice exam in office hours in preparation for the exam. So same procedure, same exam procedure that you're familiar with. So there shouldn't be any surprises. And this is the 4th regular exam. You get to drop the lowest score out of the 4 exams, but you must take them all. If you don't take an exam, you're going to get an incomplete. So you can't drop an exam that you skipped. And so make sure to make the exam. And of course, you can't drop the final as well. So you can look in the syllabus and you can see that your grade is composed of 60% best 3 exams, 20% final exam, and then another 20% for other stuff, including homework, PLAs, clickers, etc. Yes. You good? Okay. Yes. Yeah, a couple of you have not gotten grades yet. I just need to sit down and finish it. I'm sorry. It's just taking me a little bit. I'm working on a really big proposal for ion transport. So if you want to hear about proton transport, it turns out I got a lot of ideas. So I can give you a lecture on that in exchange for being super late under grading, but I promise I will get it done. And you will know exactly where you stand before you take exam 4 in the class. And of course, I'm going to really hustle to get exam 4 graded and squared away. And you're going to know exactly what's up as you go into the finals week. Yes.
When will you drop the exam?
So I am just going to drop it when I calculate the final grade. So I have a little spreadsheet. I put everything in, and the spreadsheet decides what your lowest grade is, combined, written, and oral, or written and multiple choice. Remember, every exam so far is out of 26. Exam 4 is going to be out of 26 as well. So it's combined, and I'll drop the lowest score that you have. So you can figure out what that is. And I mean, I'm not going to give you a heads up on what your grade is going into the final, but if you want to calculate it, and if you want to say, I think I've got this, and you want to check it with me, if you've done some homework and tried to figure it out, I'm happy to talk about it just to make sure, especially if you're missing stuff, especially if there's some issue. I want to sort all that out before finals week, because it's really hard to fix that at the end of the semester. But we have plenty of office hours. We've got plenty of times to chat. You can email me through Canvas so I see it. You can schedule a Zoom with me. All that stuff is great. Let's do that all before finals week. And then I'll have a couple of office hours on finals week. Then you take the final, and then we can clean anything up that we need to. But the university really wants me to give you a final, and then within a couple days, give you a grade. And so I don't want any loose ends hanging. Let's talk about any issues in the next couple weeks before we get to finals week. Yes.
So for the exam that drops, is it like just one exam, or is it like one piece from each?
No, it's one exam. So out of 26, so exam one's out of 26, 2, 3, it will be the total for that exam. So you don't get to drop like a multiple choice from this exam and a written from that exam. Yeah, you just get to drop one exam. But you must take everything. And if you're missing homeworks or something like that, why don't you turn those in late just to show me that, you know, you're being conscientious about getting all your work in. But you can't skip the final and you can't skip an exam. That is a road to getting an incomplete, I promise you. Any questions, comments? Okay, so I'm gonna expect to see lots of people in office hours. Let's work through whatever we need to work through. And of course, you remember that the final is cumulative. And so now is a really good time to start refreshing your memory in terms of what we've done over the course of the semester. Yes. No, the final is a little bit longer because remember the final exam period formally, if we're going to sit down and do it on paper, is an hour and 50 minutes. So the final is likely going to be 30, 35 questions and maybe 4 written questions. So you do want to make sure you've got like 2 or 2.5 hours to take the final. So it will be a little bit longer because it's a longer exam. Yeah. Questions? All right. I know it's really easy to concentrate on classes and get organized when the weather is turning like this, but we only have a little ways to go. So we were talking about the modulus of polymers last time, and what you should take away from this slide is you should have some appreciation for the quantitative modulus. So this is E, which is denoted as Young's modulus. And you know that Young's modulus is the initial slope of the stress strain curve. Sometimes that's called stiffness because you're not deforming the material a lot in the Young's modulus region. And so that's the stiffness of the material. And you should have an idea that rubbery materials with low TGs are in the low megapascal range, definitely below 50 or so. That's a rubbery material. They've got low glass transition temperatures, not a lot of crystallinity. Glassy polymers have a much higher glass transition temperature and a much higher modulus because of that. So glassy polymers are in the thousands, 3,000, 5,000 megapascal range or so in terms of Young's modulus. And the reason that polyethylene is in the middle is, remember, polyethylene is really crystals that are holding the material together, which are really high modulus, plus some rubbery amorphous fraction, because the TG of high density and low density polyethylene is rather low. TG of polyethylene is about what? Give me a ballpark number. Minus 60, minus 40, minus 80. It's hard to measure because there's so much crystallinity, but the TG is rubbery. So polyethylene and polypropylene have rubbery character at room temperature, but it's the crystals that hold everything together. All right, PMMA is more polar than polystyrene. They're both glassy. They both have glass transition temperatures about 100 degrees Celsius. But because PMMA is polar, what are the interactions that make PMMA even more stiff than polystyrene? What do we call those in a polar polymer? Dipole-dipole interactions. So the IMFs in polymethyl methacrylate, or the dipole-dipole interactions, are greater than what kind of intermolecular interactions are there in polystyrene? Dispersion, London dispersion forces, van der Waals forces, because polystyrene is a non-polar polymer. So in the glassy regime, as we add polarity, the stiffness goes up a little bit because the IMFs are higher. And then finally, we have phenolic resins, which are glassy and they're covalently cross-linked, so they're very stiff. Now remember, stiffness, because it's in the Young's modulus region, doesn't give us an idea of the strength or the strength at break. So since Young's modulus, I want this slide. Since Young's modulus is talking about this slope right here, we don't have an idea as to whether those polymers are brittle, whether those polymers are very strong in terms of ultimate tensile strength. And so we need to see the stress strain curve in order to figure out how tough they are, how much they elongate before breaking, things like that. And so don't equate Young's modulus with some of these other properties that we have to read off of the full stress strain curve. And so you want to have an idea of stiffness of materials, because that really gets at the intermolecular forces between the polymer molecules. And you want to be able to interpret a stress strain curve. So if I say, please draw a stress strain curve for an elastomer, or please draw a stress strain curve for a brittle epoxy, you have an idea what those look like. And remember the elongation here, this can be like, let's say 200% elongation, or the strain would be 2 or something like that, right? Delta L over L. So make sure you can calculate strain equals delta L, how much you strain it, over L naught, the original. That can be expressed as a percent or just a dimensionless fraction. Questions? Okay. And then finally, we got to semicrystalline polymers. So we talked a little bit about polyethylene and polypropylene last time. And what's really interesting with these polyolefins, of course, polyethylene and polypropylene are the most made polymers on the face of the earth. They're made from cheap petrochemicals, ethylene and propylene. And so if you design a part out of a polymer for your boss in industry, your boss is going to say, do you think you could make this out of polyethylene or polypropylene? Can we get the right mechanical properties? Because those are the cheapest and those are the most abundant. And so as you increase the percent crystallinity, the density goes up because crystals are more dense than the amorphous region. But also, since you're putting in crystals, the modulus goes up. And so rather than in megapascals, these are in 0.01 gigapascals. So you have to be able to move around a little bit in terms of the metric system. But now you can dial in the percent crystallinity of the polymer and its mechanical properties, which is really useful. So you can make different molecules to adjust the crystallinity. You can put in branching. You can make linear low density polyethylene, which has very short branches. You can make long chain branches. So branching can influence the crystallinity, but what else can we do to the polymer to change its percent crystallinity? Say we're stuck with one polymer. This is the polymer we have. How can we change its percent crystallinity? We can change the temperature, or we can change the thermal treatment, right? Because the polymer only crystallizes between Tg and Tm, we can hold that polymer at temperature or even anneal that polymer at a given temperature to get a certain percent crystallinity, and then we can quench it and go on from there. And so even though room temperature is still pretty far away from Tg, polymers like polyethylene and polypropylene crystallize really, really slowly at room temperature. And so maybe we hold polyethylene at 80 degrees Celsius, let it crystallize, get up to high percent crystallinity, as high as it's going to be, then bring it down to room temperature and we're set. And that's one of the key handles that people who process polymers use in order to dial in this percent crystallinity. Also, what do you think happens if we take polymer melt? What's the equilibrium conformation of a polymer as it's in the melt? What do the chains look like? Are they elongated at equilibrium in a polymer melt? They're all coiled up, right? So they have some coil, as we saw in the random walk. But say, what if we have this polymer in a melt and we stretch it, or we stretch those chains out? What do you think is more favorable for stretched chains? They can crystallize, right? If we start to elongate those chains in the melt and we're in the crystallization temperature region, those chains are like, well, I'm kind of extended already. I have a lower energy pathway to crystallize rather than unwrapping a coil and having to crystallize from that. So also shear or stretching can induce crystallinity. And that's another handle that people use in order to change the crystallinity of polymers when they're processing them. Has anyone ever heard of injection molding? Yeah. Anyone heard of blow molding? A little bit. Yeah, you can check out all these polymer extrusion. You can check out all of these polymer processes on YouTube. It turns out there are some great polymer processing videos on YouTube, but they do blow molding or they do injection molding and design in the shear when they're doing this molding operation to really get those chains aligned and to increase the crystallinity. Because of course you want to do polymer processing quickly because you get more parts per hour. And so shear is another important way that you get crystallization, and we'll talk about that in a second. All right, any questions? Yes. So this is Young's modulus. Young's modulus in units of GPa. So that's not a divided by, that's axis label and unit. It's just old convention. Rather than putting the unit in parentheses or comma, you see all sorts of weird stuff. This is just how that's done. Other questions? Okay. So elastomers. Remember, these are 10 MPa Young's modulus. And it turns out that cis 1,4 polyisoprene is the major component of natural rubber. And for a long time, we had natural rubber to make car tires or other rubber bands, elastic in clothes. It turns out back in the day, clothes weren't hardly elastic at all. So it was a really big deal when they started to figure out how to make rubbery materials out of natural rubber so you could have some elasticity in your clothes. And so trying to figure out how to make synthetic cis 1,4 polyisoprene was really important. And so that's artificial rubber that tries to mimic what naturally comes out of the rubber tree. But cis 1,4 polyisoprene has good elastomeric properties, and you need to lightly cross-link it. Because of course, natural rubber, does anyone know what natural rubber looks like coming out of the rubber tree? White. It's white, it's a milky substance, it's a latex. But you have to cross-link, you have to get rid of some of the water, and you have to lightly cross-link that in order to get a material that rebounds. So it's lightly cross-linked, and because it's cis conformation, it has low crystallinity because of poor packing due to cis conformation. All right, trans 1,4 polyisoprene, you can make this synthetically, and it turns out that the easiest thing to do when people started to polymerize isoprene was they made a lot of trans polyisoprene, and they're like, this stuff isn't a very good elastomer at all, until they figured out how to adjust the conditions to get mostly cis. This is not elastomeric at all, because we've talked about trans chains are more linear, or at least more regular, and so they have higher percent crystallinity, and so this makes a really bad rubbery material. All right, so that's important for elastomers, including this idea that elastomers generally have low crystallinity, because if we're talking elastomers, that means they stretch, and crystals don't stretch. And most elastomers, except for really interesting thermoplastic elastomers and some others are lightly covalently cross-linked. In natural rubber, what is the covalent cross-link, or what do we use to covalently cross-link natural rubbers? Anyone know? Historically, what did Goodyear do in his waffle iron? Has anyone heard of vulcanization? Yeah. What's on planet Vulcan? A lot of it. Sulfur. So Goodyear called it vulcanization when he added sulfur and dried out natural rubber to his waffle iron, and he pressed it and said, oh, I can make this cool rubbery material. And so natural rubber has traditionally been cross-linked with sulfur. Now you can use peroxide. There's other ways to cross-link rubbery elastomers, but vulcanization was one of the first ways to cross-link natural rubber in order to actually get a rubbery material that you could use. Okay. Oh, you can check this out. Oh, here we go, vulcanization. So in your advanced polymer classes, you'll hear a lot about thermoplastic elastomers. You'll hear about physical cross-linking, other ways to accomplish this same task. We won't talk a lot about that in this class. Does anyone know what's special about a thermoplastic elastomer? So based on its name, what do you think a thermoplastic elastomer can do? Well, what does the thermoplastic do in general versus a thermoset? So with the thermoset, all set, we can't reprocess it, right? We can't reform it. But a thermoplastic, what can you do with any sort of thermoplastic? You can melt it down and reform it with heat. You can't do that in materials that are covalently cross-linked. So this is a type of elastomeric thermoset, which means we can't reprocess easily. And that's a big issue because it's really, really hard to recycle automobile tires because they're all covalently cross-linked. You can't melt them down. You can't do anything with them other than grind them up and make athletic tracks. And so with thermoplastic elastomers, you could actually melt them down and reform them. And so there's a lot of interest in elastomers that you can reprocess easily. It just turns out that TPEs or thermoplastic elastomers are more expensive than some of the thermosetting elastomers. All right, and so of course these covalent cross-links hold the chains together and they allow the rubber to recover. So cross-links are needed in elastomers to hold low TG flexible chains together. Remember, if a polymer has a low TG, it's liquid-like, so it could just flow if you don't connect the chains together. But either through physical cross-linking or through covalent cross-linking, if you have a low TG elastomer, flexible chains, you need to tie some of those chains together so it will spring back. Otherwise, if you take an uncross-linked elastomer and stretch it, it just stays stretched like a liquid and doesn't do anything else. Yes?
What did the ones with the gaps represent? Like where?
Oh, these little loops?
Yeah.
Yeah, so
There's not dots instead of intersection.
oh, right here.
Yeah.
This is an entanglement. Entanglements are not permanent. They can unravel, and we'll talk about this idea of chains can slide past one another in terms of stress relaxation and other things in a second. Yeah,
Are crystalline and
entanglement.
branching
Oh,
same thing?
no. So crosslinks generally tie two different parts of the chain together or two different chains together. Branching is just one part of the chain goes that way and another chain is this way. So it's not a crosslink unless that branch connects to something else. So you can identify crosslinks sort of by things that look like this. Whereas we don't know where this thing is connected to. That might just be a branch. That just might be sitting out there. This thing is definitely a branch because it's not connected to anything on the other side. So crosslinks are connected to two chains. Yes.
So we said that elastomers are lightly cross-linked and this is normal cross-linking. What defines lightly cross-linked?
Yeah, it's qualitative, so just a little bit of cross-linking or high molecular weight. We can also define molecular weight between cross-links, which let's do a thought experiment. Let's say we have a high molecular weight between crosslinks. And then let's say we make another sample that's got low molecular weight between crosslinks. So few crosslinks or a lot of crosslinks. Which material do you think has a higher modulus? One with lots of crosslinks or the one with low crosslinking? Lots of crosslinks. So crosslinks increase the modulus. And so if you take natural rubber and put too many crosslinks in, it's too stiff. Or if you lightly crosslink it, it'll be nice and flexible. And it turns out if you go buy rubbery materials, there's a specification called durometer. So sometimes they report modulus, but lots of times they report durometer because it's an instrument that you put on the surface of the rubber and it tells you how hard the rubber is. So it's related to the modulus. And so higher modulus elastomers have more crosslink. Yeah.
So during the last class, we talked about the HDPE.
Yes.
The polymer should not be branched to make a high percentage of percent.
That's right.
Then can we say it is highly crystalline?
Yeah. So HDPE is highly semi-crystalline, 70 or 80%. Low density polyethylene is less crystalline than HDPE, like 50 or 60%. Yeah. But those are not elastomers because they're too semi-crystalline to be elastomers. Most elastomers don't have hardly any crystallinity at all. Good questions. Other questions? Yeah. Yeah, so loops just show that cross-linking is non-ideal. So there's some loops. Sometimes there's cross-link between chains. Sometimes you have that coil and the cross-link finds the same chain. So cross-linking can be really dispersed in terms of how the cross-linking reactions go. All right. So this is a really interesting trick, and you might have actually done this in junior high physics class or in high school chemistry class. And so if you can find a real natural rubber band anymore, and a fat one, what you do, and this is on YouTube, you hold the rubber band to your lips and you stretch it. And you can actually feel it get warmer, which is really interesting. And so that's been studied in detail. So there's been scientific measurements from this paper in 1942, when they were trying to figure out how polymers worked on increase in temperature. So this is change in temperature from, let's say, room temperature as a function of percent extension. And it shows you that this rubber band is going to get up to 10 degrees C or K hotter when you extend it over 500% elongation. You can really feel a change in temperature of 10 degrees K. And so the question is, why? And so let's see. Yes, so I have a clicker question. All right. So you can get out your clickers. CD, of course. So when we stretch a rubber band, does the entropy of the elastomer change, and how does it change? I know we have more than 45 people. So first of all, is stretching a rubber band positive or negative delta G? When you stretch a material, are you putting energy in or is it giving energy out? Putting energy in, right? And so it's not a favorable process. So what's the sign of delta G when you stretch a rubber band? Positive. Good. Which symbol is entropy? Delta S, right? That's entropy. And so when you stretch an elastomer or you stretch any polymer, what are those chains likely going to do during stretching? They're going to be more ordered, right? They're going to be more elongated. Is that positive delta S or negative delta S? Negative delta S. So we're putting more order in, which means the entropy goes down, right? Negative delta S. Stretching induces elongation of chains, and that's less disorder or more order. And so delta S is negative. More ordering means entropy is going down. Okay. Oh, sorry. Get your answers in. The question is, so we've got that positive here. And so negative T delta S, this whole thing is going to be positive, right? Once we get the sign of T in there, because that's always positive. So the question is, when the rubber band heats up, because it's giving off heat that you can feel, that's going to be the enthalpic part. What is the sign of delta H for a process that gives off heat? Negative. Rubber band heats up. So how can delta G be positive when delta H is negative and T delta S is positive? What do we know for sure has to be true? The magnitude of T delta S is greater than delta H. And so we could say that entropy is dominant in this process and delta H just plays a small role. That's important, knowing when the signs conflict, we can say that this is an enthalpic dominated process or this is an entropic dominated process if you have different signs of those two. So that's really interesting because we know that T delta S, or the magnitude of T delta S, has to be greater than the absolute value of delta H in order to make delta G positive. Okay, you can finish ringing in if you need to. So because we can do that analysis, and the key part of it is remembering it's negative T delta S, which gives you overall positive, then you can figure out what's going on with delta G. So that's just a cool aside. The question is, why is delta H negative? It's exothermic, that's good. It's giving off heat. We know that from the sign of delta H. But what's happening with the chains or the rubber band that, I mean, why is there any delta H at all? Nope.
Because the chains are like bumping against each other, like intermolecular forces.
It's not quite intermolecular forces, but the chains are doing something. When you pull on those chains, they align, right? And when you align chains, they have a better chance of doing what? interacting and making a crystal. So when something crystallizes, what is the sign of delta H? Negative, gives off heat, right? So this negative delta H is usually ascribed to what's called strain. So negative delta H is exothermic. It's usually subscribed to strain induced. Crystallization. So the crystallization part is the exothermic part, and the strain induced is the stretching, right? Strain means I'm moving material. There's some elongation. And so when I elongate those chains, they have a better chance to crystallize. They're still low TG, so they crystallize and give off some heat. That's really interesting, and that goes into how you dial in the crystallinity sometimes for different polymer processes. Yes?
So when you release it, does it like uncrystallize?
Yes, we're going to talk about that in a second. Yeah, when you release it, the crystals go away because the driving force for those chains to coil up is higher. Yes?
Does it also play an effect when you stretch the rubber, the chains become thinner, so it's easier for them to split as well?
The chains do not become thinner. What becomes thinner when you stretch the rubber band? Just the thickness of the rubber band, right? And that's the chains. Once the chains go from a coil, you know, the chains start as a coil, and then they stretch out, they're taking up less room across the width of the chain, and the effect is the material gets thinner. But the chains are the same thickness. It's just they go from a coil to elongated, and that's what causes that shrinkage in dimension. That's related to the Poisson's ratio. Yeah. Yes. Does the elongation change? Well, the chains, so the chains are coils here at equilibrium. And they're a little stretched out here. Or let's say a little elongated. And they're more elongated here. So there's a correspondence between how far you stretch the material and how elongated the chains are. So you stretch the material more, chains are elongated more. Does that make sense? All right. Good questions. Any other questions? All right. So when you let go of the rubber band, what happens? So you stretched it here, you get strain-induced crystallization. You form crystals. Material gets stiffer. Notice this slope goes up, right? So if we look at the local modulus there, that's not the Young's modulus. Young's modulus only happens way down here. But if you look at the instantaneous or the local modulus, when that curve turns up, the material's getting stiffer because you're building in crystals as you strain it. And then when you let it go, it takes a while for those crystals to melt, and you get hysteresis because of that. So anytime you see a loop like this, we always call that a hysteretic loop. It happens for lots of reasons. And so is this elastomer shown on this slide, is this an ideal elastic solid? That's my question. No. What's the definition of an ideal elastic solid? A linear relationship between stress and strain is ideal. So this is non-ideal when you elongate, because of course you have strain-induced crystallization. And it's not ideal when you let it go because it has hysteresis. And eventually those crystals melt and it comes pretty much right back to zero. Not all polymers do, but there's no permanent set in this stress strain curve because there's no permanent deformation or no plastic deformation. Okay, let's keep going. All right, we've talked about that. This is just another diagram. We're going to combine the viscous behavior of liquids and the elastic behavior of solids. You've heard that story before. Okay, so we have a scientific definition for creep. We have a scientific definition for stiffness, strength, etc. Oh, sorry, I meant a scientific definition for toughness. Now we're going to talk about creep, which is a scientific phenomenon that actually happens in almost all materials, but it's especially interesting in polymers because this gets at the viscoelasticity of polymers. So creep is defined as the change in deformation, change in elongation, delta L versus time. So theoretically, I have my polymer sample, doesn't have any load on it, it has a certain length. I put a 5-pound weight on that polymer sample, and right away, I get a delta L, right? That's the stress strain part of the curve. You put any load on a polymer sample, you're going to get a delta L. So you get stress strain from that. But then if I leave that 5-pound weight on there and I wait as a function of time, I get what's called creep. And it's a descriptive term, which means the sample is slowly creeping and getting longer and longer and longer as I hold that load on. The question is why? What's happening to the polymer chains as I hold that 5-pound load on it? Why does the sample keep deforming as a function of time? What are the chains doing? They're slowly stretching out or they're slowly relaxing. So chains are slowly stretching out, which causes disentanglements and that's called chain relaxation. So this is a little complicated because when you initially deform that sample, the chains stretch out a little bit, but they really want to be in their equilibrium conformation. So they start to coil back up. And in order to get the chains to coil back up, they need to disentangle a little bit because the chains are actually trying to get to their equilibrium conformation. And what that causes is a lower modulus material and it gets longer and longer and longer. And so this sort of creep behavior is really important, especially for applications where polymers are under a constant load, right? You know, so you build a building on a cement foundation and that cement doesn't creep very much, right? Because the building generally just sits there and doesn't do very much. But if you built that building on a polymer foundation, slowly, just like silly putty, the foundation would start to creep and the building would get lower and lower and lower until there was no foundation left, right? So you can sort of see creep if you put a ball of silly putty on the table and just because of its own weight, it creeps and flows. Yes?
Is there a general time scale of polymer creep?
That is a great question. So how fast does silly putty creep? If you make a ball of silly putty and put it on the table, how long does it take to make a pancake? Pretty fast, 15, 10 minutes, 20 minutes. If you leave it on the carpet overnight, it's completely in there. So creep can happen within, you know, a matter of hours or minutes. Say you take a piece of polystyrene and you make a ball of it and put it on the table. How fast is that ball of polystyrene going to turn into a pancake? really, really, really slowly, right? It will happen eventually, all polymers creep. But the rate of creep has to do with the glass transition temperature, the crystallinity, and the cross-linking of the polymer. So low TG polymers creep quickly, high TG polymers that are really stiff creep slowly. Yes?
What are some treatments that can be done to the polymer to like make the creep, I guess, either not occur or occur slower?
Yeah, so you can change the cross-link density. That will change the creep, right? More cross-links give you less creep. You could have a new polymer sample with higher TG, right? That will impact the creep. Higher loads will creep faster. Lower loads will creep slower. Things like that. Yes.
Are thermosets susceptible to creep?
That's a good question. So do thermosets creep? Who says yes? Raise your hand. Who says no? Thermosets don't creep. So it turns out that thermosets creep just a little bit, but they're really, 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 really slow. When I was a kid, they had a vulcanized piece of rubber in this plexiglass cone at this museum. And they would measure year after year how much that rubber sitting in this plexiglass cone creeped. And it was like, you know, half an inch over 30 years or something like that. So thermosets creep really slowly because those molecules are all stuck together. Yes.
Is it fair to say that all materials creep?
I think all materials creep, but I'm not 100% sure. I'm sure, you know, diamond probably doesn't creep very far, right? Okay, but you want to remember the definition of creep, and you want to make sure that you know what the strain versus stress looks like for these different situations. So for a perfectly elastic solid, because it has a linear stress strain curve, you put a load on an elastic solid, it elongates, take the load off, goes right back. So this is the purely elastic response, and the stress strain curve looks like this, right? So here's stress, and here's, that's not the symbol for stress. Stress strain for purely elastic. What creep is it's both an elastic and a viscous response. So a purely viscous response looks like this, which gives you permanent deformation in a liquid when you deform it. So if you deform honey, it doesn't snap back, right? Honey's just a viscous liquid, so you deform it and it stays deformed. Silly putty, you deform it, let it go, it snaps back a little bit, right? Depending on the time scale. And so if we put these together, purely elastic response and a purely viscous response, what happens in creep is that you get an elastic at short time. You put that 5-pound load on and it deforms a little bit. You get the creep behavior here. Creep elongation. You take the load off, you get an instantaneous small elastic response, and you get some recovery, and you permanently deform the sample in creep. So this is complicated. Thinking about this, thinking about the situation, and then comparing and contrasting that with what happens in elastic solid, what happens in a viscous solid, and then this is the viscoelastic response. And we'll go through some other types of viscoelastic responses like this to round out the end of the mechanical properties of polymers. All right, thank you very much. See you on Friday.